Hi everybody, and welcome to week 8 of BIOB20. So we're just done with the group activity. So thanks very much for those who participated. I think it's going quite well. Like I was saying, for people in the room, the results of the experiments are pretty spectacular in the sense that based on last week's experiment, 100% of the people who were in the room got the right answer, 100%. And people who were not in the room, it's close to 0%. So there's really a very, very strong effect. Of course, people who are outside the room say, yeah, the teacher told them. But you guys who were in the room, you know I didn't say anything. Right? It's because as simply as it is, we share much more information in person than we do online. I wish that online was able to, make us able to interact much more, but it's not the case. We can brainstorm much more efficiently in person than online. So it is possible online, but that's quite difficult. So what we see with Sarah is that, for instance, that the groups that we have in class here, they are really operational, and there are some criteria to say that a group is operational. The groups that are online, the forums, they're not that much, in the sense that there's a lot of copying the wrong answers, etc. The dominance of it's a much more dominance of the wrong answers, and for the same with the same criteria at the midterm, I could see that very often the right answers were unique and the false answers were copied multiple times. That tells me that whatever method you have to interact online is much, much less efficient than the methods you have to interact in person. So my advice is either develop better methods to work together online or work in person. So that was it for this very interesting observation that we had with Sarah. Another one, very general comment about accessibility. So for those of you who don't know, this is a service for people who have disabilities. This is an amazing service. If you have any sort of disability, temporary or permanent, I really advise you reach out to them. Your secrets are safe with them. This is not released automatically to the teachers and to anyone else, actually. So if you have a disability, you can register it with them, and I or neither any teacher will know about it. It's only when you decide to disclose it that this will be disclosed to me. So there's really no reason, if you have any sort of disability, to not reach out to them. You will be penalized to have a disability if you don't reach out to them. If you reach out to them, you have the choice to either use it or not use it. For this course, if you have an accessibility, like all of my courses, there's no in-person exam. And so many times these accessibility accommodations come with a % extra time at the exams. So a reminder is that this does not apply for take-home exams. So if you have a % extra time, by default, it doesn't apply to take-home exams. You have to ask for extra days, but you have to ask for them. They're not automatic. And the final thing is that accessibility services always needs note takers. Note takers or volunteers, students in the room who take notes for people who have difficulties taking notes because they have a broken finger or something like this, or any other reason. In this class, of course, this is recorded, so I don't think that this is particularly relevant for BIOB20. Maybe it is. You guys will tell me if you think that this is needed. So if anybody feels like they can help and they want to volunteer, don't forget that there's not only BIOB20, there are many other courses where you can be a note taker for someone else, and that is hugely appreciated when people are note taking for some other people. So if you have a good soul, think about it. Also, I checked at my fame on YouTube. I already have 4 likes for video 3. So I don't know what I did on video 3, but apparently that was very good. So if you guys like the video, please tell me what I did, because I got no idea why it was so popular. So now let's start with the class proper. So today's theme is ranks and Wilcoxon-Mann Whitney U test. And so we're going to follow up on last week's group activities, which was mostly about using the function rank. So the way we're going to start is I'm going to spend about an hour explaining how ranks work and how how to use it for the Wilcoxon-Mann Whitney U test. And after this, I'm going to spend approximately 30 minutes giving you some new R functions, some new tricks that you can use, so that you can also develop your R vocabulary and the way you code. In the meantime, interrupt me as usual. Like if you have questions, don't let anything be misunderstood as I'm explaining things. I'm here really to explain, so interrupt me, ask your questions. But even before I start, maybe you have questions about things you'd like me to explain again or to discuss, or that were not clear from everything that we've seen up until now. Online as well. You guys can go ahead, of course, and ask questions. Amazing, everything's clear. Okay, well, if everything's clear, then let's jump right in with the ranks, and we're going to study the function rank here. So let's give a very simple example. We're creating a vector x in which I'm putting the numbers 1, 2, 3, 4, 5, but not in that order. Okay, so I'm going to actually maybe just do sample 5, which will give me the numbers in the order 3, 5, 1, 4, 2. And if I call the function rank on x here, I get pretty much exactly the same output. Okay, so the function rank here is not really a very good example to show what it does exactly. So I'm going to give another one with 5 Gaussian random numbers. So I'm going to say that x is, oops, just 5 Gaussian random numbers. Remember, the Gaussian random numbers by default here, they're close to 0, and they will very rarely go below -3 or above +3. And if I now call the function rank on x, then I got these particular values here. So what is it? It is the position of that particular value here in the sorted order. So that'd be 3. So if we look at this here, this in the sorted order, that's indeed in position 3. And so that's why it gets rank 3. So in that silly example here, of course, the third number for the numbers that are between 1 and 5, well, that's number 3. So kind of silly. We learn more about what the function rank does here. So basically what the rank function does is what you would expect it to be. Say I have a couple of people who have run a race, and like they're sorted by their family name, so they're not sorted by their score at the race. And so I call the person with family name starting with A, and if this person is ranked 7, well, that's the 7th shortest time from below. Okay, so sort in ascending order. So the small values here and the large values here, and the rank is where they are in that sorted order. Very simple. I mean, you know what a rank is, right? You've been graded all your life, so you can have an idea what I'm talking about. So the rank function is pretty straightforward, at least so it seems. So one thing that we can do with the function rank is now to merge the ranks from two different sides. So we could take two samples and then we merge their ranks together. And that's what we had in the group activity last week. So I'm defining, for example, a function, a sample y, that'd be, again, from a Gaussian distribution. Could be anything. Really, this is not only about Gaussian distributions. So those are my two samples here. And if I pack them together into a single vector, I got a vector of length 10. And you can see that because I write it this way, x and then y, I got first the values that are from x in the order of x, and then I get the values of y in the order of y. This is really what the concatenate function does in R. Like you just stitch things together in whichever order they were. And if I do now the rank on that, you could see that, for example, the ranks that correspond to the element of x here are the first 5. And they're not the same, of course, as the ranks just of x. Here I get numbers that can go anywhere between 1 and 10, and here they can go only between 1 and 5. I hope that's clear for everybody. Once I merge the things together, then of course the maximum number have doubled if the samples have got the same size. So far it's kind of all relatively simple. And the main point of why would anyone want to do this, compute ranks, etc., is because now we can use ranks as a proxy for the difference between the two samples. If you remember, we've seen the t-test last week, and we have applied the t-test the very first time to just compare whether something is equal to a target value. That was in the example of the proton gradients. Like you wonder whether the value is 0.35 or 1.35, I can't remember. And so you have a target value and some uncertainty around that target value. That's one way of using the t-test. It's called the one-sample t-test. But very often in real life, you don't have a one-sample problem. You have a two-sample problem. You have ran like a particular experiment, and you have a control, and both of them have got some uncertainty, and you want to compare the control and the experiment. You have a placebo and a vaccinated arm, or whatever that is. So the typical scenario in experimental sciences is that you have not just one, but two samples. So the standard way of using the t-test is really that you got two samples, you want to compare them and know whether one has got a higher average than the other, or whether you can consider that both of them are pretty much on par with each other. And you guys remember what is the one theorem that really allows us to use the t-test a lot? The central limit theorem, right? Like that's the only theorem we've seen, so it's pretty easy to remember that it's this one. And there's one condition with the central limit theorem, which is, you know, like it's nice, but also not so nice, is that you have a big data set. And so nowadays, data is very big. We're in the era of big data, but this is not always possible. Sometimes you cannot have a big data set. And so in that case, you're stuck with using a t-test, but if your data originally is not Gaussian and your data set is small, then the central limit theorem will not just kick in yet. We have seen examples when we take the exponential distribution, it can take rather samples of size 30 before the average starts to look symmetric and Gaussian. If you're smaller than 30, the skewness of the original data will remain. So there's no universal number, but let's say if you're 100 and up, very often you can consider that the central limit theorem will just give you a very good Gaussian approximation. But if you're in the realm of, let's say, sample size of 10, 15, 20, up to 30, you're in the danger zone, in the sense that the central limit theorem will not really apply, and you're again finding yourself without really a good test. So the hope is that ranks will allow us to solve that. So why would that be the case? When I take two samples like this, the X and Y, they were taken from the same distribution, and so their ranks, as you can imagine, they're going to be comparable with each other. Like the values in X are going to be very much like the values of Y. So if you merge them together, sort them, then you say, are the ranks of X below those of Y? There's no reason why this should be the case. So in that particular example, we can see that the ranks of X go from 2 to 9, and the ranks of Y go from 1 to 10. So they really both span kind of the whole range of ranks that they could. But if we're now going to slide a little bit, one of the two samples to the right, let's say that the sample Y that was here, I'm going to take the same values, but I'm going to add a very large number to it, 100. Okay, so now the values of Y are not at all comparable with the values of X. And so when I'm now going to compare the ranks of X and Y, which of the two samples is going to have the greatest ranks? Y. Okay, like all the values they're all strictly much higher than the values of X. So if I compute the ranks of both X and Y, you could see that here 3, 1, 4, 2, 5 could be any order, in the sense that the values of X, they're all taken from the same distribution, and therefore they have no particular preferential order. But for sure, the numbers 1, 2, 3, 4, 5 are going to be on the left, because those are the values from X, and the numbers 6, 7, 8, 9, 10 are going to be on the right, because that's the values from Y. Okay, and these values here, this particular order could have been any. It's just that because those are the samples that come from Y, then they're going to have a high rank. I'm going to give another example of here where I'm going to plug directly the numbers here, just to hammer that in. So n equals 5, but I'm adding, let me put a bit of space here, but I'm adding a very large number here. Okay, so whenever I do this all the time, there's no chance that the numbers coming from Y here will have any of the ranks 1, 2, 3, 4, or 5. They're just so far apart that there's no chance that one of the values will be kind of, in the other pool. They're just way, way too far apart. Also, it doesn't have to be 5. If I take 8 here, so the numbers go to 13, but still, it doesn't change anything that the first 5 values are just so far from the next 8 that the first 5 numbers are going to be on the left side, then a break, and then you get the next 8 values that are all on the right side, but in an order that's irrelevant, immaterial, because within the sample Y, they're exchangeable. So the idea is that maybe we could use the ranks instead of this Gaussian approximation to tell us that if we compare two samples and we merge them, take the rank, and then separate the ranks from, those are the ranks that come from X, those are the ranks that come from Y, and if the ranks that come from X are way below the ones from Y, that gives us the idea that the samples were kind of far from each other, regardless of the actual value that separates them. Okay, if the ranks are much lower in X than in Y, then they were separate. And you could see that, you know, here I can put not 100, but I can put 1 million. It doesn't change very much. The numbers are still the same exact numbers from 6 to 13 here, and 1 to 5 there. So at some point, we have decoupled, in a sense, the magnitude of the effect from really the relative separation between the two samples. And so that's the hope here, is that we're going to get a criterion which is going to be much more universal than using the Gaussian approximation, that either requires that we had Gaussian numbers to start with, or that we had enough of a sample size to kind of get the mean, which has this typical Gaussian shape. That's the hope, but we need to think a little bit about it. So what we had last week in the group activity is that when we use two samples like this, so a Gaussian random sample here and a Gaussian random sample there, I think everybody got the intuition after a while that these numbers that are here, do they have a particular order, or a preferential order? Not really, right? And so we all get that intuition from somewhere that this is all symmetric, that there's really no reason why the numbers 1, 2, 3, 4, 5 should be preferentially on the left side this time. You know, the two samples are kind of symmetric. They're all completely, you know, the order seems to be completely relevant, and that's actually correct. So when we do this and that, we're actually getting exactly the same answers. If I take the first 10 numbers and I put them in a random order, I'm doing exactly the same thing as taking a sample, another sample which has the same distribution, merging them, taking their ranks, and then seeing the order of the ranks that I got. Okay, it's kind of weird to say that this command here is exactly the same as this one, but that's what we mean when we say that the numbers that we get when we take the ranks of two identical samples like this have no particular order. The numbers that have no particular order is just take the first 10 numbers and then shuffle them, and then that's it. You get a particular order. So everybody got this intuition, at least after a while staring at these commands. And so it doesn't really need proper justification because we all have that intuition. But still, with the justification, it works better. And you should never take my word for anything. So like if we say that is probably here the same as just taking a permutation, the term is a random permutation of the first 10 numbers, we still need to verify. So why is it the case? Well, when you think about it, let's take my samples X and my sample Y. Okay, how do I change the order of the elements from X? It's sample X. Okay, so if I do that, I just get the same numbers, but I keep changing the order. So that's what I'm doing here. And if I'm doing sample Y here, well, here my Y is not a good example. I should recreate another one, which is from the and now I get the same numbers, but I'm kind of shuffling them like that. Okay, so far so good for everybody. So when I got or norm 5 on the left and or norm 5 on the right, it's really exactly the same as saying or norm 10. I hope that everybody agrees. Okay, so here taking 5 Gaussian random numbers and then 5 Gaussian random numbers independently is really exactly the same as saying I'm taking 10 Gaussian random numbers from the beginning independently. So it's the same as saying that we take the ranks of just that. Come back. Rank or norm 10. That's literally exactly the same as that. So now we just need to say, why is it the case that when I take the rank of 10 Gaussian random numbers, I always get the same chance of getting any order? Well, let's call this XY then. And the point I want to make is that here, when I sample XY, then I'm shuffling the elements. But let's say, what is the probability of obtaining these particular numbers? How do I get that? This is d norm XY. Okay, so mean equals 0, standard deviation equals 1. So those are here the probability of getting these numbers. Now, if I want to get them in a different order, then here, these are the probabilities of the same numbers, but in a different order. Right? So that's exactly what we do here. Remember that d norm really gives us the probability of obtaining a particular number. I'm just checking the probabilities for each 10 of them. But what is the probability of obtaining that particular sample as taking the product? So I get that. And of course, when I shuffle the numbers, now it doesn't change anything anymore because I'm taking the product, and the product, by definition, doesn't care about the order in which they are. So in the end, the reason why the order is irrelevant is just because of the way we compute the probabilities. Of course, we're not equally likely to get that particular sample of 10 numbers or another particular sample of 10 Gaussian random numbers. But if we can get them, if we get these samples with these numbers, then we have exactly the same chance of getting them in any order. Okay, so that's the reason why, in the end, when you do rank R norm 10, you do get a completely random ordering of the first 10 elements. Yeah, like we have the intuition, which is okay, that's what it should be, but the justification is because the probability, given that you fix the 10 numbers from the Gaussian distribution, you have exactly the same chance of getting them in any particular order. And so if you now average this over all the possible Gaussian random numbers that you can get there, it doesn't change anything. You still can get them in pretty much any order, just because the product doesn't care about the order. So that's the reason why our intuition actually matches that very simple phenomenon, that when you take any distribution here and you rank the elements, just because of the way we compute probabilities, then we're going to get here a random shuffling of the first 10 numbers. And when I do this with a uniform distribution, well, it doesn't matter, it's the same. You know, the fact that these are all from the same distribution, that there's no particular asymmetry in what I'm doing, that forces the fact that we're going to get a random ordering of the first 10 random numbers. And of course, I could take literally any distribution that I like. It's the same for the exponential. Like it's going to be completely symmetric. And I see these, there are like a concentration of 10 on 9th column, but this is completely irrelevant. So that's the rational justification. Now let's go a little bit at greater length into demonstrating it by actually plotting it. So one thing is, okay, we have the intuition, we have some sort of a rational, but this rational is still a little bit patchy. We have been just playing with R norm, with ideas, but we have done a proper theorem. So let's just see whether we can get an idea of how to represent them in a graphical way. That's going to be much more satisfactory. But before we do this, are there any questions about this? All right. Okay, so let's go ahead. The first way we're going to do this is really to get an idea of what is the perfect sampling. When I do sample 10 here, I'm getting a little bit more succinct with my notation as the classes go. That just gives me a random ordering of the first 10 numbers. And if I do replicate that, you can see that now I get a matrix where every column that I'm going to get is a random ordering of the first 10 numbers, the first 10 integers. So what I can do is I can just resample this a couple of times. Let's say 1,000, maybe 10,000, and then I can try to find a way to represent where the values accumulate. And we know the answer. They're not going to accumulate anywhere. Like they're going to be completely shuffled through the 10 positions. So vertically, these are the 10 possible positions, like first rank, second rank, third rank, etc. And the numbers that they get is their rank. And we pretty much know that every rank can be at every position with equal probabilities. But first, we need to get the observation. So let's say I'm calling obs for observations, and I'm going to set that I resample this 10,000 times. That takes a bit, but not too much. And so I've got now a very long matrix with 10 rows and 10,000 columns. And each of these columns represents one particular resampling of the order of the first 10 integers. Okay, so now I'm going to use ggplot in order to create that particular plot. We're going to see how to do that. And remember that in ggplot, you always have to think, what is my data frame? I need to make a data frame. And so the way we're going to create that particular object is to say that we need to keep track of the positions. And at each position, we're going to give a rank. So the first position, let's say I'm calling something pos position, and that would be 1 to 10. So the vector pos here contains the position 1, 2, 3, 4, 5, 11, 10. And if I take, for example, obs first column, I get these numbers here. So my first record is that the positions 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 got ranks 4, 9, 2, 7, 6, 1, 8, 10, 5, 3. And so we're going to replicate these data into a data frame to say, like, okay, that was the first round. But then on the second round, position 1 is going to be associated with 7. And then in the third round, position 1 is going to be associated with 3, etc. So then I'm going to make a data frame with 2 columns, only 2 columns. And the first column is going to be the rank. Second column is going to be the position. So I'm pairing a position with a rank. And I'm going to have 10,000 such pairs. Times 10 is 100,000 such pairs. I'm going to make a lot of pairs. But it's kind of weird to think that what we need to do is to take this data, which is like a very big matrix, like with 10 rows and plenty of columns, and then to transform it into a data frame with 2 columns. And maybe as I'm going through this, then it'll make it more concrete and make it a little bit easier for you to understand how that goes. So we would, what we need to do first is to say, I'm creating the ranks, and so I need to extract them from my matrix obs. So how do I do that? Well, it's quite simple. This is as vector obs. So if you look at now, how does this look? It's just one vector, and the elements are in the order that I want them. 4, 9, obs, the first 3 columns. Okay, so that's 4, 9, 2, 7, 6, 1, etc. So you see that I'm going column after column. If I go here a little bit bigger, let's say 25. So those are here, those are here the first 10 numbers that correspond to the first column here. And then the next 10 numbers that you get here, like 9, 4, 2, 1, 10, you see that this is the second column, 9, 4, 2, 1, 10. So when I do this, when I take a matrix and I say transform that into a vector, what O does is that it reads them column by column. So it starts with the first column and then puts the next column below and the third column yet below, etc. So I get exactly the same numbers as in my matrix there. And 10 in a row here correspond to one particular record, and the next 10 another record, etc. So that's the values I get for the ranks. It's really what I've resampled. Now for the positions, what is it? It's always the same thing this time. It's number 1 to 10, but I'm repeating them times equals 10,000. So if I look at the first 25, you could see that, okay, well, I get 1, 2, 3, 4, 5, 6, 8, 9, 10, and then I get this 10,000 times because I've resampled 10,000 times. I'm just making a data frame here that has the ranks associated with their position. And that will allow me to plot something interesting with ggplot2. So I'm ready. That equals data frame. So I need to create the name of the columns. The first is going to be called ranks. And that here will be ranks. I already defined it. And pause equals pause. I defined them both. So that gives me a data frame with two particular objects. And the one way I want to plot these things is to say that on the x-axis, I'm going to have the position, and on the y-axis, I want to have a stacked bar that shows how many times you obtain a particular rank at a particular position. So rank is going to be used for coloring. And remember that if you want to do this, you need to make rank a factor to say that the rank is not a number, it's not something you can add anymore. This is just a label. Rank 1 will be red, rank 10 will be yellow, etc. So these are just a way to make a particular object into a label. It looks like this. In the end, the dimension of the data frame are 100,000 and just two columns. And these two columns are all the pairings that I obtain during my simulations. And now I'm ready to make the ggplot. So library ggplot2. As well. And now we're ready to make the plot. So ggplot, remember, ggplot. The first is your data frame, and then your aesthetics. And we say x is going to be the position, so that's a numerical variable between 1 and 10, so it's going to be nicely on the x-axis. And fill is going to be ranks. So fill is for the coloring. So that's what's going to be in my plot. And we say geom, which is a histogram, I think. And one particular thing is that if I want to stack them, then I need to say position equals stack. So that in principle should give something. Okay, complaints, but it works. Coming. All right, so that's the way it should look. I don't know if you could do it at the same time as me or if that went too fast, but we get here the positions here on the x-axis. We get the position from 1 till 10, and each position now is filled with their rank. So you know how many times did it get rank 1, 2, 3, 4, 5. So you got 10 colors here, and you can see that this is pretty much what we expected, right? That every position gets pretty much every rank 1/10 of the time. So that is what a uniform distribution really looks like when you represent it this way. Just a few things. There's this really annoying warning here all the time. In that particular case, it's not just an annoying warning, it also distorts a little bit the display. That you see there is this kind of ugly looking space between the bars. It's because it has made 30 bins and it uses only 10 of them. So if you say bins equals 19, that's a way that you get actually nice spacing between the bars. There are 10 bars, 9 spaces between the bars. So that makes a nice looking spacing this way. So that's just working on the aesthetics. And you can see that with 10,000 resampling, we just get each segment is pretty much exactly identical with each other. But that's what we expected because we have just resampled the perfect randomness. We have just shuffled around the numbers between 1 and 10. So of course that looks like this. Now, that was the standard. We need to compare that to the claim, which is that when we do taking the ranks of or norm 10, then that's exactly the same thing as doing that here. Okay, so here that's the command that says just take 10 random numbers and shuffle them. And now we're not doing this anymore. We're going to say take the rank of or norm 10, and that's it. So that also runs fast. I need to recreate my data frame here. And when I plot the sample here, I pretty much get the same thing. That's a new plot, but it looks indistinguishable from the previous one. So that's kind of an empirical demonstration that when you take the ranks of 10 Gaussian random samples, it's exactly the same thing as shuffling the 10 first numbers. And just to hammer the point one more time is that when we take not just the Gaussian random sample, but the uniform distribution, for instance, I recreate my data frame, then still doesn't make any difference. It does not matter which distribution I have taken, I always get the same thing. So far so good? That's just a visual representation also to give you a little bit more exposure with ggplot2, which is a very powerful library. But on the other hand, the structure of the calls can be quite difficult at times. Any questions so far? Okay, good. So now we've seen that how the ranks work. So far, nothing particularly counterintuitive. I'd like to speak about the things that are a little bit more counterintuitive and that are creating a lot of pain for people who are using ranks. So the first thing that I'd like to show is what happens when you do that. Maybe I'm going to take, I don't know, like 4.3 and 4.3. Okay, when you have a vector of size 2 with two elements that are equal to 4.3, and you take the rank, what do you get? You have 1.5 and 1.5. Does that make sense? Not quite. Why do you say it doesn't make sense?
It makes sense in the sense that they're both the same, so you can't rank them. But
yeah, okay.
I don't entirely understand the 1.5 within it.
Yeah, okay.
Well, because one of them is rank 1, one of them is rank 2, so it's
right. Exactly. So in the end, it's taking the average. So here, what happens when you have 5.7 here? So 4.3, 4.3, 5.7, 1.5, 1.5. So it's really weird to get this fractional rank because why? But yeah, that's the argument. They have the same value, so they should have the same rank. They came at the end of the race at exactly the same time. You can't tell them apart. So they must have the same rank. And the problem is that if you say they're both 1, well, what is the next? Is it 2, 3? So the way this works is R by default gives the average rank. You said 1 would be 2, 1 would be 1. So together they're 3. You split that in 2, each gets their half. So they're 1.5, both of them. And the nice thing is that now when you take the sum of the ranks, this is 6 here, and if you can tell them apart, that one of them is 4.1, it is still 6. It doesn't change the total sum of the ranks. That's the idea. So when you have ties, the default behavior of R is to give them the same rank and to give them the average of the ranks that they would have if they were separate. So if we take now 3 values, they each get 2. Okay, it'd be 1, 2, 3. Together they have 6. Divided by 3, that's 2. So not necessarily super intuitive at first, but after a while, you make peace with that output and you accept that, okay, that's the way it is. They all have the same rank, they're indistinguishable, and we want that the property that the sum of the ranks would not be changed, so it's still 2. So what would be the next here? There's another value, which is 10. So the rank of 10 is going to be what? 4. Okay, so like the ranks would be jumping in that case. There's no rank 1, there's no rank 3. You go directly from 2 to 2, 4. But again, the sum is 10, and it would be 10 if you were able to tell them apart. So first thing, ties are possible. They happen, they're very unlikely with Gaussian, with exponential, with uniform. But when you start to rank things like Poisson or the binomial distribution, yeah, for sure you're going to have ties. So remember that the default behavior of R is to not break ties, just to give them the average rank. Why is that so complicated? So here, ties method, you go average, first, last, random, max, min. So you have plenty of options of what to do with the ties, but the default here is to take the average. You have also another interesting, which is random. In that case, I think you just break the ties at random. Say one of them gets first, the other one gets second, and that's the way it is. Sorry for you seconds, like to flip the coin. So you also have max. In that case, they would both get 2, and min, they would both get 1. So you have several options, but the one that is the norm, not just in R, but in the rest of the world, is taking the average. And that has to do with the Wilcoxon-Mann Whitney U test. Okay, so far so good with the taking ties of the ranks. Don't forget that ranks always have these problems with ties that can sometimes be annoying. Another thing is what happens to here missing values. If I do, for example, rank, let's say 4.5 and NA. Remember, NA means no record. Just like there should be a number, but we don't have that number. So what's going to be the output here? Of course, you can write it. It's super easy. And the problem is that NA gets rank 2. And that really makes no sense. This is such a very strange decision of the R developers, is that the NAs, they always get the highest rank. Just like that. And if you got 2 NAs, well, then they get the highest ranks, like 4 and 5 are given to NA. Does that make sense to you? No, to me neither. So that's just, I'm not sure why they decided to do that. So why is that an issue? So we go back to our favorite line of code, which is rank or norm 5 or norm 5. Oops. And I need to put them together into the same vector, like we see. Okay, but if I say, oh, these 5 elements, by the way, you know what? They were from a record that had a couple of missing values here, by the way. Well, so we have exactly the same number of records, 5 and 5 on both, but just because this one had missing values, now you can see that the ranks on the sample Y have just increased a lot. And if you're not aware that there are some missing values in the sample Y, then you're just concluding right now that sample Y is shifted very much compared to sample X because the ranks are very much higher because of these missing values. So it is very, very strange that OR has decided to just give the missing values a high number, because whenever you have missing values in your samples, in your real samples, and you will see that this happens, then taking the ranks and suddenly just saying this has bigger ranks is going to drive you to the false conclusion if you haven't noticed that there are NAs. So I can't remember if there's a way to suppress that with the NA to give a more logical. NA values are never considered to be equal. Okay, that's good, but they're still considered to be high rank. NA last, a logical or character string controlling the treatment of NAs. If true, which is the default, missing values in the data are put last. If false, they are put first. Right, so either way, it makes not a lot of sense to me. Okay, if NA, they are removed. If keep, they are kept with rank NA. So that should be what it is. Like the default should be actually that rank should, in principle, NA.last equals NA. NA here. Or was it again? And maybe with one quote. Kind of weird. No, that was keep. Yeah, exactly. That should be the way it outputs it. Like there was a missing value, it's still a missing value. It's not rank 7 or 9 or whatever this is. Okay, another one that makes a little bit more sense is this one, NA, because it removes them and that it doesn't count it, doesn't start to shift your sample for the wrong reason. But really the normal way R should behave is this one. But on that particular function, somehow the programmers seem to have made a decision that I cannot understand. Just, it's a warning. That's going to happen to you at some point. You're going to measure the ranks on some sample that has missing values, and you're going to get caught. But just once. After this, you remember, and you won't get caught anymore. All right, so far so good. Does that make sense? Any questions? if you have a string value, so what do you mean a string value? Like I go 1, 2, 3, 4, 5, and then hello? So it's a question that I didn't really go into. So let's say C1, 2, 3, 4, 5, hello. So is that even going to run when I press enter? No, it's not an error. It's just fine. So even before you rank it, you have to understand what happens. The fact that there was one string value inside the vector, because the vector is allowed to have only one type, then OR suddenly changes everything to one type. And that type cannot be number because there's no number that corresponds to hello. But there is a string that corresponds to 1. So it says, I'm just taking over the control, and then without telling you, I've transformed all of that into strings. Now if you rank them, the rank of strings is not the numerical order, this is the alphabetical order. So like you just use another order, which is the alphabetical order, and you get that. So it kind of works, but you're not comparing numbers in the alphabetical form and not in the numerical form. So recipe for disaster. Like this thing, you can get horrible confusion, horrible bugs if you miss that. But still, that's what OR does. It doesn't complain, it goes ahead with that. And to some extent, I have to agree with the choice that were made there. They're a bit dangerous if you don't know that OR silently changes the type of your data if there's one element that's wrong. That's typically happening when you read in very large data in OR, a large data frame, with millions of rows or something like that. Maybe not millions, but tens of thousands. That you have numerical, like a numerical column, but then, there's one number with a comma, and that comma, it should be a dot, but because it's written by someone from a country where they use the comma instead of the dots, then, well, now this is text. And so just because you have one comma in the whole column, then the whole thing has been turned into text. So that's very typical. Disasters always have a high chance to happen at the beginning when you import the data. You could have a whole class on data import. It'd be a bit boring, but for sure it'd be useful. So that's the main dangers with ranks. Remember the ties and the NA. The NA are particularly dangerous. So now we're ready to see how the Wilcoxon-Mann Whitney test works. Let's go back to our favorite example here, when I'm going to remove all these complications with the NAs. And remember that the first 5 numbers here correspond to the ranks that are coming from X, and the next 5 numbers that are here come from the numbers that are in Y. So can you guys think of a statistic that we could use based on these ideas that we've been floating so far to tell whether there is any discrepancy between the ranks in X and the ranks in Y? Online as well, you're allowed to contribute ideas. And Charlie is allowed to contribute either online or in person. The mean of the first half and the mean of the second half. Okay, that's an excellent idea. Okay, so you would take, for example, the mean here of the first 5 numbers, 10, 4, 6, 7, 5, and the mean of the second half. So if the null hypothesis is true, if the 2 samples are really coming from the same distribution and they're indistinguishable, what do you expect from these 2 means? Are they going to be similar, dissimilar? What are your thoughts? Similar, okay, yeah, because this is just, any of the 10 numbers can be on the left or on the right. When you take the mean, there's no reason to believe that on the left, they're going to be smaller or bigger. Now, if the 2 samples are very far from each other and one of them is shifted by 300, what do you expect about the means here of the first 5 that are here? Is it going to be the same, bigger, or smaller than the mean of the next 5? Smaller, right? It's pretty obvious. So we can use that. We can use the mean of the ranks that are coming from the first half and the mean of the ranks that are coming from the second half. So that is up to taking the mean of the sum. That's pretty much the same, depending on how you normalize your distribution. This is the Wilcoxon-Mann Whitney U test. So that's it. Take your 2 samples, merge them together, take the ranks, and then you take the mean rank on the left half, or the sum actually in the real test, but we're going to use the mean. Take the mean and you minus the mean of the other half. if the difference is close to 0, then your two samples were kind of aligned. They had pretty much the same centering. If the means are very far apart, it's because all the ranks on the right side were much bigger, for instance, than the ranks on the left side. And the two samples were very far from each other. And you can reject the null hypothesis that they're coming from the same distribution. So very simple. So what are the advantages of this particular approach compared to the t-test? Anyone sees it? Or not really? The first is that this works all the time. Okay, like doesn't matter whether your sample is big, small, etc. This works literally all the time. The second, I mean, all the time in terms of the number of elements in your sample. The second is that remember that here it doesn't matter whether I have or norm here. I could use or unif or exp. It doesn't really matter. So it works not only on every sample size, but also on every distribution. So I'm not making any particular assumption about the distribution of my sample. It could be Gaussian, could be binomial, could be anything, and I don't need to have a large sample size. So this is kind of, in a sense, this is a very, very impressive technological achievement, the Wilcoxon-Mann Whitney U test. That there exists kind of a universal test that you could say, yeah, it pretty much works all the time. Like there's not a very, very few cases that I know of where you cannot use the Wilcoxon-Mann Whitney U test, because it really manages to strike such an essential and universal feature of distributions that you don't need these assumptions. They were quite weak for the t-test, huh? You know, to say just get more data and you can do it. But with the Wilcoxon-Mann Whitney U test, you don't even need that. So this is called a non-parametric test. This test, okay, non-parametric. So what does it mean non-parametric? Is that maybe the term distribution free is better chosen, is the fact that it does not make assumptions about a particular parameterization of the data, right? Whether it's Gaussian, exponential, or something like that. So that's the idea. How does that make sense for you? Any questions about yeah, go ahead. So your question is, can we not just take the mean? Can we see the discrepancy between different samples? That's tutorial 8. Right, so this is exactly the point. You're going to be comparing the t-test and the Wilcoxon test. And so at some point you will see whether there is any difference between them, whether there's any advantage, etc. So that's really the topic of tutorial 8, is to, of course, disclose and explain how the Wilcoxon-Mann Whitney U test works. But now that we're quite comfortable already with OR, etc., we can dash much faster on the preamble, null hypotheses, statistic, etc. And so we'll have plenty of time in the last questions of the tutorial to really compare what happens with the t-test versus the Wilcoxon test. And you will see it's very, very informative. I have to say that I keep discovering things as I prepare these tutorials. You know, the more I, when I start a tutorial, I think, oh yeah, it's going to be super easy. We're going to do this, this, and that. And then I realized, oh, I was completely wrong about this test. It's actually not at all what I thought. So it could be that I'm learning even more than you guys when I'm teaching that. So for me, it was quite surprising to see the difference between the Wilcoxon-Mann Whitney U test and the t-test. And it's one of these plots that I'm asking you to make was an extremely big surprise for me. So yeah, didn't answer the question, did I? And that's on purpose, because that's exactly the burden of tutorial 8. Any other question that I can answer, maybe? If not, let's make some progress. So here, how did people actually, Wilcoxon on one side and Mann Whitney on the other side, how did they make up that test? So let's give an example here. We know that if the null hypothesis is correct, these ranks here, they just, sorry, null hypothesis correct would be without the plus 300. Huh? So now the numbers are just a random shuffling of the first 10 numbers. So when we take the mean of the, let's say I call this ranks, so that's one iteration. So now I want to compare the mean of these 5 numbers with the mean of these 5 numbers. Well, that's what we say. So how do I do this? So that's mean ranks 1 to 5. So that here is the mean rank of the sample X after merging, and the other one, that's 6 to 10. It's 6.6. And now my statistic, the U statistic should be the sum, actually. Yeah? That'd be, well, we choose one versus the other, so it doesn't really matter which ones we use as the standard, but that'd be that. So that's minus 2.2. Okay, so far so good. So like I just could resample very easily these ranks here. One way I can do it is by saying I resample them this way, or I could say I resample them this way. It's exactly the same. I just take the first 10 numbers and then shuffle them completely at random. And doing that, I'd compute my score this way. And this time it's 3, etc. And so what I would do is that I just resample a lot, see what's the value of my statistic, compute my null distribution as usual, and then I got my, like the histogram of the null distribution. So we can do this. This is fairly simple. I'm actually asking you to do this in tutorial 8. But let's think a little bit, just for a while. So here, I have 10 numbers, sample 10. So before we could use resampling, Mr. Wilcoxon and Mr. Mann and Whitney, they could not really use the same strategy. Still, this test has been around for, I think, since the 1940s. So they were able to compute this particular statistic, the null distribution, etc., fairly accurately. So let's think about it. How many ways are there to arrange 10 numbers? 10 factorial. Okay, so is that a big number, small number? Pretty big, right? So of course it depends on the expectations, but like the number 10 factorial, well, we're going to compute it. We're going to see what it is. So that's, the function is factorial. So that's approximately 3 million, okay? 3.6 million, approximately. So 3.6, 10 to the 6. So that's 10 factorial. So when you think about it, if Mr. Wilcoxon or Mr. Mann and Whitney wanted to actually, get that test right, they would have to explore 3.6 million ordering just for 10 numbers, and they would have to compute their probability of occurrence. Well, they're all equally likely, but that's kind of fairly complicated when you have just pen and paper. Like, there's really no time to do this, and that's just for 10. Of course, when you have slightly bigger samples, like 15, the numbers become like just impossibly big. So they did not have the option to just look at all the possible arrangements and then say, we're going to weigh them and see how often we get into that value of the statistic or this value of the statistic. Like way too much work. So the way they did this was something different. And actually you can do it with much less effort. So when we take the example again of the ranks here, and so we put them here with their positions. So we have 10 positions to fill. Okay, so rank 1, rank 2, etc., rank 9, and rank 10. You don't really need to say which order they are. You could say, I just need to tell which are the ranks that are belonging to sample X and the ranks that are belonging to sample Y. So let's say, for example, rank number 1 here is in sample X, and I'm marking the ones of sample X here, and rank number 9 as well. And the ones in the middle, of course, I would have to tick 5 boxes. And so now, once I tick these 5 boxes, doesn't matter which order they are. They all, I'm going to get exactly the same value of the statistic. Is that clear for everybody, that the sum of the ranks is going to be the same? So how many ways are there to take 5 boxes out of 10? Yeah, if I choose 10. Okay, so, and if I choose 10, so I think it's choose, oops, 10, 5, I think. 252, so that's a much smaller number now. So already that, well, okay, that's a lot of time, and you can compute the statistic by just going through these exact 252 possible cases, right? So it's much smaller. We're not talking of millions and millions, but you can do even better than this. In reality, what you need is to say, I don't need to compute the whole thing. I just need to compute the cutoff at 5% or at 1%. Okay, so all those numbers here, all those particular combinations, they're all equally likely. So 1% of 252, that's 2.5. Okay, so when you have actually chosen which are the 2 or 3 cases that are the most extreme, right, that are the most on the left or on the right of my distribution, but that's enough. That's all you need to do to be able to say that's my cutoff here at 1%, for instance. So in reality, you just need to say, what is the score here when I tick all the first 5 boxes here. So 1, 2, 3, 4, and 5. When I do this, I got the most extreme scores. Okay, it means that the sample X had ranks 1, 2, 3, 4, 5, and sample Y has got some ranks 6, 7, 8, 9, 10. So when I do this, I got the maximum discrepancy between the 2 samples. What is the way that I create now the second biggest discrepancy? How would I do that? Well, it's when I don't tick this this box here, but I tick the 6. Okay, that's the way to get the second biggest score as possible. So here I can compute the score, which is the maximal, like really extreme. There's no way to get a bigger score or the smaller, depending how you put the sign on the distribution. And then I get the second biggest, and I can work my way here until I have total 1% of the cases. And when I have done that, then I got the cutoff. And whichever score was the one that counted to 1% of the cases, then this is already the score that is at the 1% cutoff, or the 5% or whichever cutoff you have. So in reality, you just need extremely few cases, and you go systematic with that by just being clever about the way you count the events. And so that's how the test was made. Like they needed to count just a few cases by a strict enumeration. The tables were available already from the 40s with extremely little investment. So that's really an incredible piece of engineering, this Wilcoxon-Mann Whitney U test, in the sense that this is both extremely simple to compute and extremely universal. So that solved really so many problems around in terms of testing. Many people that I've met say that's the only test I do, because just why would you do anything else? You got a test that's both easy to compute and universal. Come on, like stop thinking about it. Tutorial 8 will maybe make you change your mind about this, but I see the point. This is a very good argument. This test is kind of almost a magic bullet. So what about when the numbers go much bigger? Like, can you do the Wilcoxon-Mann Whitney U test on huge samples? Well, we're going to find out. So one thing is that there is this thing called Wilcox.test. It's such, again, a very weird choice of R. Like the name of this test is kind of Wilcoxon-Mann Whitney U test. I think because there was a quarrel about who was the first inventor. And I think in the end, it was decided that it was Mann and Whitney, but Wilcoxon was kind of, everybody was saying Wilcoxon test. I can't remember exactly the detail, but it's not even the name of the guy, that's just Wilcox. Like, it's just so weird that take half of your family name and not even put the last 2 letters because whatever. So, well, I find it a little bit weird for Mr. Wilcoxon, but anyway, that's the way, Wilcox.test. And now we can fit in 2 very large samples. For example, our norm with 1,000 numbers here, and then another one with 1,000 numbers. And that works just fine and actually quite fast on top of it. So when the numbers are really big, it's not by strict enumeration anymore, because now you have much bigger than choose 5. You have 2,000, or here I put even 10,000. 2,000 choose 1,000. That's not the same number. Now you really have to go through a lot of possible cases. So there's a good approximation. That is a Gaussian approximation. So in the end, it's kind of a t-test, actually. At the end, when the samples become big, using the fact that the central limit theorem even applies on the ranks, because you're taking the average of the ranks, it still works. And so from somewhere around 100, it starts to use the t-test. And so you're back to what you had before, sort of the t-test, basically. So it still works, not a problem at all. One thing is that sometimes you do get a warning when you use the Wilcoxon test or the Wilcox.test. If you do, I'm taking the numbers 1 to 10 here, and the numbers, let's say 5 to 15. You see warning message in Wilcox test default cannot compute exact p-value with ties. So you do get a p-value here, but it tells you that I really cannot compute something that's exactly accurate if there are ties. And that has to do with what we've seen, the fact that ranks and ties, like for them, it's really difficult. So you do get a test, it's fine, but you still get the warning that this is kind of hard to know what would be even the definition of p-values when you have ties. You can still take it as that. So most people just ignore that message, say, yeah, whatever, just give me my p-values already. So beware that this is what this message here means, that the p-value is kind of up to definition for that particular case. When you don't have ties, it doesn't complain. So or norm 10 and or norm 10, like we're very unlikely to get any ties. But that has to do with the fact that internally, so you see no complaint, internally, Wilcox.test says that it takes the rank internally and then computes the sum. So that's, in a nutshell, the way the Wilcoxon test works here. Yes. That's the score. Okay, it's not taking the mean, it's taking the sum in the original test. Doesn't matter, you know. It's up to it's really up to a normalization in that particular test. So they just chose to compute the sum, and then they computed their cutoff based on the sum. But if you compute the mean, well, that changes the distribution completely. You know, that shifts much closer to 0. But it's still, as long as the distribution matches the score that you compute, it's fine. So that's something that we've done multiple times. And many people who know statistics are a little bit confused by BIOB20 because they say, well, that's just not correct. You know, that's not the proper statistic. And the answer is no, it's not the proper statistic. No, I know. So why are we not giving the proper statistic? Well, that's also a point I want to make, is that we don't have to. The reason why people used the proper statistic when they were doing statistics before, like before 2015, let's say, is because you need that particular normalization to compute the null distribution. Otherwise, it becomes hard to compute the null distribution. But we don't care because we just resample. So if you agree that my score is that, and I'm multiplying it by 7 because I'm in the mood for 7 today, well, my null distribution is going to be multiplied by 7. My score is going to be multiplied by 7, and nothing changes. All that matters is that the score that you compute is exactly the same as the one you use for the null distribution. It doesn't have to be the exact chi-square score, the exact student t score, the exact normal distribution score, the exact Poisson approximation score, etc. We're much more free than people who are using pen and paper, because very often with pen and paper methods, you do need one particular form because other forms are just not computable. So very often I've taken a lot of freedom with these computational forms, and I've always used the simplest. In particular, for tutorial 7, what I call the student's t-statistic is not the one that most people have seen. It's not exactly the same. And I really don't care. My student t-test is as good as anyone's student t-test. It's a little bit less good than the one of odd, I have to admit. But because the statistic was simpler, I chose this one. And the null distribution was not exactly the same, but the score was also not exactly the same. So in the end, the compensations match up exactly. So talking about computing the null distribution and the score here, we need to find a way to create that statistic. So this is explained in the tutorial, in tutorial 8, but I'd like to do that with you because that involves getting a little bit more advanced with functions. So remember how I define a function. I would say my function f, for example, is a function of the parameter x here, and I would say something like x squared. I've got a fantastic, useful function. If I do f of 3, wow, wow, 9, incredible. Okay, so this is nice, but come on, that's a little bit kindergarten. Like these are really very simple functions, and it's time to grow up, and we need to make like real adult functions. So what's the difference between a baby function and an adult function? Is the fact that usually there are more than just one statement in a function. And the example that we're giving now with the statistic of the Wilcoxon-Mann Whitney U test is typically one where we need more than one statement. So we're going to write together the function that will compute this difference between the mean ranks. So remember, the first thing is that there are not just one element, but two. We have x and y, sample x and sample y. But originally, x and y are just raw numbers. The first thing we need to do is merge them, take their ranks, and then take the mean of the first half and the mean of the second half, and take the difference and then return that. So how do we do this? We start, like the first step is we take the two samples, we merge them, so let's see x, y. Now that's the concatenation. That step is easy. Second step that's relatively easy is we rank it. Okay, so that here gives us the numbers like the merge and the ranking. So that function here is already quite useful. If we do f or norm 5 or norm 5, well, we get already a shortcut here of take these two samples, concatenate them, compute the ranks. Now, how do we continue that function? Is there a way that we can find a function here, wrap this into a mega function that we take the first half and then take the mean of the first half and then take the mean of the second half and do the minus of these two? I'm not aware of any such function that does that. So we need to go one step at a time. So we start to be facing the fact that we need to write functions that will have several statements in them. So the way you do this in R, you have two options. Either you still, what? Semicolon, exactly. So that's the first option is you still want to make not a baby function, but a teenage function, which means it will still hold on one line and I can put my multiple statements with a semicolon. So like this is just normal OR. It's the same as inside the session, the OR session that you have. You could say the ranks here is that. So you have proper assignments inside the function. And then how do you get the first 5 ranks? As ranks 1 to 5 here. But it's not the first 5 ranks that you want. Okay, here you know that x has got size 5, but in general, you don't know the length of x. So you have to say here length of x. And that would be the ranks that correspond to sample x. Okay, so you need to do that. And so that'd be, for example, ranks x. So you define them this way. But you also need to define the ranks of y. So you continue with a semicolon here, and you keep going. So the function is going to be a little bit too long. It's going to be what we call sometimes a spaghetti function, like very, very long, and that's not particularly nice coding habit. Real programmers, real adult programmers, that is, have a trick. They use multiple lines. So there's both advantages and disadvantages in using multiple lines. The main disadvantage of using multiple lines is that when you're working like this on a terminal, is that you need to reintroduce them every time. There's no way to kind of paste very easily for me all the lines together. But if you're using, for example, RStudio, then this is much easier. You just like paste them in your RStudio and you can execute them all together. But for me, working with this very old-fashioned OR here, I would have to type every line at a time. But here we go. I'm not lazy, and we've got a bit of time. So I said that the first thing is that I define ranks here as the rank of C, X, and Y. We've done this multiple times now, so we understand what happens. In that case, I don't need a semicolon at the end. I'm just using the fact that every line is one statement. So I'm making a multi-line, multi-statement function. So ranks are here, then the ranks of X, I define them now from ranks, take the value from 1 to length of X here, and the ranks of Y, I'm taking the ranks now. It needs to be from length of X, they're together in length of X plus 1. Okay, like we went to the end of X, and then the first after that is the first element of Y. up until the end. So we can say here length ranks, for instance. So we're going from length of x plus 1 till the end of the vector. It's not really elegant coding, or it's perfectly horrible for that compared to Python, for instance. Or you could say that doesn't make sense, it's unreadable because you've got length x and you've got length ranks. So logically you have to say length x plus length y. And that makes a little bit more sense. But then that's a fairly long command for something that's fairly trivial and a lot of round brackets. I'll still keep it. So I'm offering a little bit more elegant solution in the tutorial 8. It's not more energy friendly in a sense, but it's much easier to read. Is that you compute the rank of x and then flip and then compute the rank of y, so that the coding is actually avoiding this horribly unreadable thing that's here for a relatively trivial operation. Okay, we're done here anyway, so the final statement will be ranks x minus rank y, or the mean minus ranks y, and because it's the final statement, it's going to be the return value of the function. So you will see in the tutorial this multi-line statement, because I couldn't think of a way, I'm not sure that there is any, where you can, with one single short snappy line, compute the statistic. I always found solutions that need multiple statements. So there's nothing wrong with multiple statements, just fine. And as things go, we need to develop a little bit better coding habits, and that's completely normal to have functions with multiple statements in them, for loop inside the function, if statements inside the function, etc. And now we can easily, in principle, with a bit of chance of like it will even work. Yeah, almost now. So here I made typos, of course, and I need to recreate my whole thing. This is the disadvantage of a multi-line function here when you're coding at the terminal like that. So where is the typo? It's here. And with a bit of luck, this time it's going to work. Fantastic, minus 2.6, etc. So I can now resample my score relatively easily with that. That's what you're going to do. You're going to define that function. It's written in the tutorial 8. You don't have to come up with it yourself. That's to avoid typos, actually. So you'll be able to get the null distribution and then run the Wilcoxon-Mann Whitney U test. Before finishing, I'd like to introduce to you something that's both fun and useful. It's the function identify. So very often in R, you have some data. Let's say X is 100 Gaussian numbers, Y is 100 Gaussian samples, and you have to plot X and Y to determine some fantastic, wonderful things about your data. And you're saying, oh my God, this point here, which is there, is so interesting, because you know it's less than -2 on the y-axis. It's above 2 on the on the x-axis and above 2 on the y-axis. This is so interesting that I would like to know what it is, of course. And the problem is that you have 100 points, and before you can know which of these points is really associated to that, I mean, which of these values that you have, these numeric values is associated to that particular point, it's not going to be always easy. Okay, let's say imagine these are people, and like you want to know what's the name of that person here that corresponds to that outlier. How would you do that? You can spend some time trying to find a way to identify this point. So there's this really nifty function which is called identify. So you say identify here x comma y. So you pass exactly the same thing as what you've plotted here. And when you press enter, so you can see here that this little wheel keeps turning here on my Mac. And here nothing happens. You know, I lost the control over my session. So as soon as you type identify, then you also go into a loss of control mode. And if you're using RStudio, I'm not sure what happens with identify, if it actually works or not. I think it doesn't. And I think that's the reason why I'm not using RStudio, actually. So, but now let me show you my superpower. So I just have to click here with my left click on that point, and it tells me this is 8. I'm not sure it's 8 because we don't really see very much. It could be 28, 38, or 58. You see, I can click on any point I want, and I can almost read what is the number. Maybe 60, maybe something else. Darn, I thought you'd be impressed, and I'm making a fool of myself now. Okay, but you get the point, right? Is that with this identify trick here, I can get the ID, the index of these particular points in my data set. So that's the way I can actually identify them. And now the problem is that I still have this spinning wheel not anymore, but I'm stuck. So how do I get back to control of my session? If you have a mouse, it's the right click. If, like everyone, you have a laptop, I think it's control click on the figure. So when you do control click on the figure, then you get back to the real world. It prints the numbers that you have identified in sorted order, not in the order in which you clicked. And then, of course, because I type all these silly things, then it wakes up and says, "Oh, difficult to do. I don't know what you mean," etc. So that's the way it works. You can use this function identify when you have a plot, a scatter plot, typically. Click on the points that you want, and then you'd say, so this point here, which was it? Well, by elimination, then we'd say that it's probably 48, okay, because like 18, 23, etc. So if you, let's do it again. Okay, I'm plotting the function. And so if you find yourself in this silly situation that, okay, you click on it, well, 48. Now, somehow it was a little bit different this time. Yeah. So much easier to identify. The point is that no matter if they did not appear very clearly here, remember that they will be printed on your session at the end anyway. And you can do even more than that. You could say, for example, those guys is the output of identify. And then they appear on screen, those guys here. And when, oh, by the way, see, when I click 2 times here on 89, it says, I've already told you what it is. And so, okay, when I'm done, control click on the screen. And you see that it didn't print as it did before, but now I've got those guys here. It's those guys. Okay, so it's a really handy function that works for identifying the points on a graph. So main disadvantage, I think it doesn't work with RStudio, but I'd like to have confirmation from anyone if you guys, RStudio works, says Marco. So, okay, main advantage that it does work with RStudio, so that's great news. Maybe I'll finally use RStudio this time. Other disadvantage, which well, there was not a disadvantage, so real disadvantage, I think it doesn't work with ggplot. And so like you really have to use the old-fashioned ugly OR plots because it's not a ggplot function, and so it's not going to do it. Maybe there is an equivalent for ggplot2, I mean, all the time. If there is one, and if anybody knows it, please tell me. That'd be quite useful. But I think this function is really an OR-only function. So that's it. That's what I wanted to share with you today. We still have 2 minutes. If there are any questions or any emergency, I think you'd like me to re-explain very rapidly. I got a request in these last 2 minutes. Yes, I think ggplot can label the points, but it will label all, exactly. So you can put all the labels and they can become a little bit overwhelming. Like choosing the labels by clicking on with an interactive interface. I've not seen that in ggplot2. Yeah, my request, yeah, go ahead.
Doesn't just like making the function, does that make does that make a function can make a function B and just have function A be part of function?
Yes, you can make a function inside a function. You can make a function that calls another function, and you can make a function that calls itself. You know, f, it's a recursive definition of function, works just fine. F depends on f, tip top. Of course, you have a way to make completely silly calls and that explode the computer. But if you do it properly, then you can make recursive functions. Yeah, works just fine. So in the last 30 seconds, my request would be, if anyone would like to contribute some ideas or to spend some time with Sarah and me to help us design the course for next year, especially because we have changed a little bit the class. We've been experimenting, as you've noticed. And so to tell us, okay, this really did not work, don't do that next year, that'd be nice. Also, if you have ideas for how we could change the first 6 weeks, which were quite different from the next 6 weeks. We're taking any feedback, so any idea that is out there for how we should run the class next year will be very appreciated. Don't wait until there is this feedback session at the end of the semester, etc. Because this is structured feedback. I'm not allowed to ask you all the questions I wanted. This feedback is not allowed. So if you have any idea, any suggestion, please, anytime you like, come forward and tell it to us. We'll be very happy. With that, it's 7, so time to end the session. Thank you very much. Good luck at the tutorial and see you next week.